So in today's video, we're going to talk about the various effects that our sun has on Earth, starting off with the solar wind and getting toward things like coronal mass ejections, solar flares, and then eventually how sun has affected our climate in the past. So first of all, the solar wind, you can think of this as kind of a breeze of charged particles coming from our sun, and for the most part they're protons, but you're also dealing with some ionized helium ions, like singly ionized helium atoms, and also some helium nuclei, that is, alpha particles. So because of the solar wind, our sun actually loses about 10 million tons of material each year. However, compared with the mass of the sun, that's only on the order of about 1/100 trillionth of our sun's mass per year. So what's important for us is that when the solar wind interacts with Earth's magnetic field, it ends up getting deflected into our atmosphere, and when those charged particles interact with the upper part of our atmosphere, they can produce these nice aurorae, which in the northern hemisphere we call the northern lights, or the aurora borealis. In the southern hemisphere it's the aurora australis. So as these particles interact with our magnetic field, a sort of magnetic bottle effect takes place, and they end up getting trapped and corralled toward these little rings that actually surround Earth's magnetic poles. So here's a nice picture of this aurora borealis. In fact, you can see some things in here that you should be able to recognize. For example, you have the Hyades in here, and you have the Pleiades over here. In fact, this is the planet Saturn in this picture. And this is the ring around Earth's north magnetic pole, where the particles kind of preferentially get corralled as a result of the magnetic field. And notice that this inside of this ring, this is where you preferentially would see the northern lights. And notice it's not directly at North's pole, and it's especially not at the center of Earth's magnetic pole, because the actual center of that is deep inside of Earth. So where those particles are going to get corralled is where the strongest field lines end up actually kind of going down into Earth itself. And notice the country of Iceland is in this, as is southern Greenland. And you also have central Alaska and southeastern Alaska, kind of around the Anchorage, Juneau area as well. So these are areas where you can preferentially see the aurorae, as well as the islands off of northern Scandinavia and northern areas of Russia. So that's what we call the auroral zone. And as Earth's magnetic field shifts, that is going to shift over the coming years as well. So just a few nice pictures for you to see. Some more. Very nice ribbon effect there. And again. And in the southern hemisphere, they really don't look any different. It's the same type of idea. These are the southern lights in New Zealand. And here's a nice auroral corona. And you can also see it in certain areas of Antarctica. Now, as pretty as aurorae can be, the things that can sometimes cause enhanced aurorae, things like solar flares and coronal mass ejections, can also be relatively disruptive for Earth. So solar flares are the first of these phenomena. Solar flares are due to what you could call explosions that occur when magnetic fields near our sun's surface reorient themselves when they're originally going in opposite directions. We call these magnetic reconnection events. We're going to talk about these in a little more detail shortly. But these can end up sending large amounts of high energy radiation, because when this happens, then suddenly a bit of material is let free, and that allows a whole lot of radiation to come toward Earth in the form of ultraviolet, X-rays, and even gamma rays at times. So that's what happens with solar flares. Solar flares happen when large amounts of high-energy radiation flare toward Earth. You'll also see that area of the sun become much brighter than it typically would be as well, but most of that radiation is not in the visible part of the spectrum. And flares are often associated with sunspots. So when these do occur, astronauts would potentially experience a lethal dose of radiation. But the good news is that generally we have a good bit of forecasting for when this is likely to occur. We don't necessarily know how strong it's going to be when it does occur, but when we realize that a solar flare is about to occur, we get the astronauts sheltered inside the International Space Station or whatever vehicle is around. So here's a picture of a solar flare. Notice the curling effect right around here. This is due to our sun's magnetic field. And nice picture of our sun in UV light. So these can also, just as they would potentially be lethal to passengers near the ISS, they can also disrupt communications on Earth. But the most damaging effects come from something else. Those are known as coronal mass ejections, which we're going to talk about soon. So same thing as with the solar wind. When the high energy particles that sometimes go along with this end up getting trapped by Earth's magnetic field, you can end up getting especially strong aurorae. And some of these expected effects can be found on this website, www.spaceweather.com. Now, speaking of solar flares, we mentioned nanoflares before when we were talking about the heating of our sun's corona, the outer layer of the atmosphere, that very hot but very diffuse region. And it is now believed that this is due to nanoflares, where you're dealing with little bitty magnetic reconnection events, and when they reform, they end up releasing energy. And typically, each time this happens, an energy associated with about a 50 megaton hydrogen bomb, think about the Soviet Union's Tsar Bomba in the early 1960s, well, this happens millions of times every second, and it is believed that these nanoflares do account for the majority of the heating of our sun's corona. Remember, we're talking about something that's a couple million degrees compared with the surface of our sun, which of course is much denser, but is only about 5,800 kelvins. Here is a depiction of magnetic reconnection. So you'll often have a long wrapped around magnetic field line coming from one spot and going outward toward another, but just due to various other effects, the field lines can get pressed close together. And when that happens, you're dealing with a lot of potential energy built up right here, and this can end up being released as energy in a new field line, so to speak, along with a burst of radiation coming from around the surface when this occurs, if these were to reconnect, so to speak. So when these reconnect, a burst of energy is let forth, and you end up getting a solar flare and or a coronal mass ejection. Now, with these magnetic field lines, you can also have very nice solar prominences. These are relatively benign events, but they can be beautiful. This is a loop of material that's caught in the magnetic field lines of our sun. So we've mentioned before that magnetic fields deflect charged particles. Well, that's what happens in the case of prominences. These can either be long-term or they can be relatively short-term in association with solar flares. So just as iron filings can trace out the magnetic field of a bar magnet, you can also get that happening in the area kind of near sunspots in the form of a solar prominence. Here's a picture of one of those, and very nice zoomed in picture with this nice loop here. The nice loop here is the prominence. Here is a very dramatic prominence where the material is actually looping in a nice spiral around the field lines in this case. In fact, something like this could potentially be used to make a at least estimate of our sun's magnetic field in that area. These things can be huge. This is our sun with a particularly large solar prominence scaled with Jupiter here, and this little dot is, you guessed it, that's Earth. So yes, these things can be very large. Now, it is possible to use direct means to measure our sun's magnetic field. And by the way, when I say direct means, I mean a certain physical process occurs, and you can use that process itself as a sort of magnetometer. And this is called the Zeeman effect. So the Zeeman effect is a situation where you end up having a splitting of spectral lines by a magnetic field. The reason this occurs is because some of the in some cases, the electrons orbiting are in the spin-up scenario, sometimes spin down, and when they interact with magnetic fields, that results in slightly different energies, so you end up getting a splitting. This is the main area, and then this is, say, spin up or spin down, and this is the other one, so you end up getting this nice splitting. The degree of this splitting indicates the strength of the magnetic field. So here we have a nice example of a solar prominence, and it's actually one of the methods that we can use to determine temperature of certain parts of the solar chromosphere, because of the fact that this gets high up into the chromosphere and therefore emits emission lines that correspond to the temperatures that you would expect, and also in terms of the thinness versus thickness of the emission lines, that sort of thing allows scientists to discern the temperature of the chromosphere. Remember, that's the layer above the photosphere. Now, it was taken at ultraviolet wavelengths, so we're talking in this case 30.4 nanometers, so that's over 10 times shorter in wavelength than what you can see with the unaided eye, so we're talking about well into the ultraviolet part of the spectrum. And here's another nice image just showing a lot of solar activity in this case, kind of building up to solar flares. And these streamers right here could be lines of kind of solar prominences just viewed kind of down the curve of the prominence itself. So we next turn our attention to coronal mass ejections. So these are the most disruptive of all of the various solar phenomena. These can lead to power grid failures during major solar storms, and some of these have had some historically important events. So when our sun is particularly active, like around solar maximum, where you're dealing with lots and lots of sunspots, you might get about 5 or 6 coronal mass ejections per day, whereas during a solar minimum, they might occur like every other day, or right now, practically not at all, because our sun has no sunspots at this moment, that is, at around March of 2020. Now, consider how big our sun appears in the sky. Our sun is about half a degree wide, so it's a disk that is about half a degree wide. Now, consider the fact that Earth is 1/100th of the diameter of our sun. So how would Earth look in the sky from the sun's perspective? Not a very big region, to say the least. Now, that means that the probability that a particular coronal mass ejection will head directly toward Earth is relatively small. Now, these things are very big. They go outward. They consume a reasonably large region in space, but still the probability that they would head directly toward Earth is pretty small. But every once in a while, it does happen. Now, one particularly well-known event that did head toward Earth was the famous solar storm of 1859. So, as you read in one of the reading articles that you had to do, this began around the end of August, but the actual peak of it was around September 1st of that year. This is the largest known geomagnetic storm, and it was caused by a very massive solar flare and the associated coronal mass ejection. In fact, the solar flare of that was so powerful that the radiation and everything from it cleared out a lane between Earth and the Sun that allowed the coronal mass ejection itself to travel directly toward Earth almost unhindered in a very short period of time. Usually these things might take a few days to reach Earth, the coronal mass ejections that is, or CMEs as we like to call them in terms of the abbreviation, but this one only took something like 18 hours, so it was a very quick result as after this very powerful solar flare. And it was the first solar flare ever witnessed. It was witnessed with the unaided eye, and that just gives an idea of how powerful this thing was. So the storm itself, the resulting solar storm, was so great that telegraph grids caught fire, and other telegraph grids could be powered just by the magnetic activity itself. So let's talk about how that actually occurs for a moment. So whenever you have a loop of wire, there is a law of nature, known as Lenz's law, that says that the total amount of magnetic flux through that loop wants to remain constant. So if there's a strong magnetic field, and you suddenly change that magnetic field, nature doesn't like that. Nature also doesn't like it if you try to change the area of that loop, or the angle at which that loop is oriented with respect to the magnetic field. So what does nature do when such changes do occur? Nature induces what we call an electromotive force, so to speak, an EMF, a voltage potential throughout that loop that causes a current to flow around in that loop. And that current can exist in a lot of different situations, and if you're suddenly changing the magnetic field strength in the general area, then that will result in a current being induced, as we call it, to try to cancel out that change, because the current itself creates a magnetic field that tries to cancel out that change. If we wanted to get into the mathematics of that, then we would get into a course on AP Physics C, E, and M. Now, there is a scale used to measure the intensity of these solar storms. It's somewhat similar to the Saffir-Simpson scale for categorizing hurricanes, where a 1 is your least intense hurricane and a 5 is a potentially catastrophic one. And the storm of 1859, which caused not only telegraph wires to catch on fire and everything, but also had very bright aurorae all the way down to the tropics, this was a 5 on that scale. Now, there was a fairly significant storm from August 7th through 10th of 2011 that was about a 2 or 3 on the scale. It got a lot of press coverage, and there was a big worry about it. It could potentially do something to Earth's power grid, but it was nowhere near the event of 1859. If the event of 1859 occurred today, it would be catastrophic damage and results throughout the world. For example, North America would be entirely without power probably for a couple of weeks or so, and parts of North America would be without power for at least months. Now, this leads to a big worry, because based on what we're seeing with the sun right now, there is a particularly devastating storm set to hit on Wednesday, April 1st of this year, and that is a 5 on the scale, and that is believed to probably be shutting down all of Earth's power grids as a result. So obviously this will be particularly bad in the midst of the coronavirus. So, April Fools, there actually is no such storm. And if there was, we certainly would not be able to forecast it 2 weeks ahead of time using present-day technology. But yeah, just think about what would happen if there was. So, nonetheless, though, there was a fairly major storm about 9 years ago, but it still was nowhere near in comparison with the one of 1859, which would be absolutely catastrophic. So, just a summary in terms of solar wind versus solar flares versus coronal mass ejections. So the solar wind is constantly going on. Our sun is constantly streaming these charged particles, mainly protons, into space. A solar flare occurs due to a magnetic reconnection event, which allows a stream of radiation to be released from the sun. We're talking about ultraviolet X-rays mainly. And a coronal mass ejection is where the reconnected field lines themselves can help to carry away bulk material from the surface of the sun. So we're actually talking about large amounts of charged particles and bits of high energy hydrogen and helium. Now, these magnetic reconnection events, well, they can also occur with Earth's magnetic field. In fact, that's the big power behind solar storms and how they can cause all kinds of nasty power surges on Earth, because when these magnetic reconnection events occur, localized areas will experience a very quick, sharp change in the magnetic field strength around there. You won't really feel it in your body or anything like that, but electric grids and everything will end up having these very strong induced currents to counteract those changes, and that can cause them to be fried. Now, unfortunately, that link that I was going to show for that video is no longer in operation. I just clicked on it, and it does not take me to the page that it took me to last year. So that link no longer works. Now, the solar wind itself interacts with the area surrounding our sun, which we call the interstellar medium. And that area itself has magnetic fields, weak magnetic fields, due to particularly just the rest of our galaxy, and it's something that interacts with our sun. Now, the place where the solar wind interacts more with the interstellar medium and begins piling up, so to speak, is due to slowing to subsonic speeds, is known as the termination shock. And the boundary between the interstellar medium and the heliosphere itself is called the heliopause. And just an update, the Voyager 1 and 2 spacecraft did encounter this region beginning in the mid-2010s. Now, it used to be believed that this led to a kind of bow shock, so to speak, where you ended up having this shock of material from faster than the speed of sound to subsonic speeds as our sun and everything with its surrounding heliosphere moves through the interstellar medium. But the Voyager spacecraft did not see any evidence of that. They did not register any evidence of that. As far away as they are, they still do occasionally make measurements and send data back to the radio telescopes on Earth. So we now believe that the bow shock doesn't actually exist. So this is kind of a old primitive version of how the heliosphere in our solar system how we used to think that it appeared, but now we realize that the bow shock isn't actually there. Instead, there's just kind of a general pause, so to speak. And we now have a newer model about the shape of this. It's no longer considered to be the shape of a comet. So this is a computer rendering of that new model, the yellow area showing what we think of as the heliosphere nowadays, and the silver lines actually are solar magnetic field lines, whereas the red lines are interstellar magnetic field lines. So as I was recording this, my daughter came down and started making some noise. So, Lily, do you want to come and say hi to the class? You want to come and say hi to the class?
Hi.
Yeah, say hi, class.
Hi, class.
Yeah, that's my daughter Lily. Okay, yeah, go on and play, Lily. Okay, so next we turn our attention to our sun's direct influence on Earth in terms of the climate. So you can figure that obviously, since our sun is the vast majority of our energy source, that it's going to play certainly a very major role in our climate. In fact, if you just had a 1% drop in solar energy output, that would result in a 1 to 2 Kelvin drop in global average temperature. Fortunately for us, or maybe unfortunately in the face of upcoming global warming, most of the changes from our sun are actually only on the order of about 0.1 to 0.2%. So these types of brightness changes, therefore, don't really have a significant effect on temperatures on Earth. But nonetheless, other types of effects that come in particular in the ultraviolet part of the spectrum, as well as the magnetic interactions of our sun, can be quite significant. Now, there was a bit of a greater amount of cooling than what one would expect during a period called the Little Ice Age. This is a period of very prolonged lack of solar activity, and this played a major role in the climate during the Middle Ages. But I will mention that most climatologists believe that the warming that's occurred over the past 30 years is primarily due to human activities, not due to natural events such as increased solar activity and that sort of thing. So here's a graph of total solar irradiance in units of watts per meter squared. I've mentioned before that the so-called solar constant at Earth is about 1,366 watts per square meter. But you can see that there are fluctuations in that, but those fluctuations are quite small, on the order of like 0.1 to 0.2%. So they are not going to be all that significant in terms of affecting our climate. They're going to have slight effects, like on the order of a tenth or so of a degree, but not major effects. In fact, notice that there is about an 11-year period with this. That corresponds to the 11-year sunspot cycle. Now, there was a period of sustained solar activity increased solar activity known as the medieval maximum. This was during the time of the Viking explorers, and this is during the time when Greenland actually was green, at least on the southern coasts, green enough that they could have farming there and everything, and one of the reasons why they called it Greenland. I mean, yeah, they called it Greenland to try to entice people there, but there was truth in the name as well. And people were able to farm in northern Canada on Baffin Island, and that's certainly not possible today. So during this time, about 1,000 years ago, at least the high latitude areas of the northern hemisphere were noticeably warmer than they are right now. In fact, this is the second most sustained period of increased solar activity of the past couple of thousand years. In fact, the strongest period of increased solar activity is known as the modern maximum, which we just got out of. We're going to have more to say about that in a little bit. But the medieval maximum was a period in which particularly the northern hemisphere of the world and possibly the entire world was about as warm as they are today. In fact, certain parts of the northern hemisphere were even warmer than they are today. Eventually, though, this would come to an end, and it would come to an end in a relatively rapid pace. So this ended up going into a period of declining solar activity, and the world temperatures cooled. There were crop failures throughout Europe especially, and the lack of a lot of these good crops ended up leading the way to decreasing people's immune systems due to less nutritious food, and this led the way to the Black Death from bubonic plague in the 1340s. When the immune system was weak, they ended up succumbing to these types of illnesses much more easily. In fact, death rates from the bubonic plague were on the order of 25% or so. Now, eventually, the temperatures got cool enough that we were talking about quite significant colder than average temperatures. In fact, some of the coldest temperatures that we had seen since the last ice age. As such, we actually call this period that lasted from about the year 1500 to 1850 the Little Ice Age. And right smack in the middle of that was a period of sustained lacking in solar activity known as the Maunder minimum, where there were almost no sunspots for a period of about 70 years. And rivers that don't typically freeze froze over, and this was just a very cold period as the climate goes. In fact, something that should be borne in mind is a lot of times when you hear certain remarks on the news about how much global temperatures have warmed since the beginning of the Industrial Revolution, it must be kept in mind that the beginning of the Industrial Revolution was the coldest period since just about the end of the last ice age, so it's not really a fair place to begin when you set your starting point as a minimum. And other people should also keep that in mind. Sometimes skeptics of climate change set their starting point as the peak of the 1998 El Nino. Well, that was the hottest year on record until 2015. So you can't really say that there was global cooling after 1998 when you pick that as the peak. So you have to keep it on mind at both ends, that you should not be picking peaks or troughs in various curves to use as your starting points of comparison. So here are the last 400 years of sunspot observations, starting with a lot of the observations made by Galileo, and going into the Maunder minimum. And then there was a secondary minimum called the Dalton minimum, and then finally when we got out of that, that kind of marked around the end of what we call the Little Ice Age. And then we got into the modern maximum. So it turns out, in fact, I need to update this number based on more recent studies, but the modern maximum was actually the most significant, what we call grand maximum of the past 9,000 years. So you can figure that, yeah, it should not be surprising if that would play a role on our climate, and we're going to talk about that soon. Not as big of a role as some people might think, but nonetheless a role worth considering. So here we have solar activity for the past 12,000 years, and we don't have this quite updated with the modern maximum, but you can see this Maunder minimum right in here. This was a very significant period in here. Now, how do we figure this stuff out? And you can see this kind of again right here. We use what we call proxies, and there are a number of proxies that we can use. Carbon-14 and beryllium-10 are particularly good proxies. So the reason that this works is because when our sun is very active, that ends up making the heliosphere itself quite strong, and it's able to repel cosmic rays that come from various high-energy events in our galaxy. And what that means is that when you have more solar activity, there are going to be less cosmic rays incident into our solar system and therefore incident into Earth's atmosphere. Well, what does that do? Well, cosmic rays incident in our atmosphere end up interacting with the atmospheric molecules and the nuclei therein, and in particular causing reactions such as changing nitrogen-14, which of course is very stable, into carbon-14, which hopefully by now in the course you know is not stable. Carbon-14 has a half-life of 5,715 years, and that itself makes it useful for dating various organisms that have recently been living, or structures that are composed of, say, logs and trees that people have cut down in the past thousands of years. And by itself, this would be a fairly accurate dating technique going back probably about 20-something thousand years or so. But not all that much further than that, because of the fact that the amount of carbon-14 present in the atmosphere, and therefore present in living tissue, changes over the millennia because of solar activity changes. So in other words, what you need to do is you need to calibrate it with something else. Well, it turns out that you can calibrate this dating technique. Tree ring dating, what we call dendrochronology, actually takes us back to about 27,000 or 28,000 years nowadays. And I mean, yeah, there aren't any trees alive right now that were alive 28,000 years ago, but there are trees alive right now that were alive 6,000 years ago. And you can compare the tree rings in those trees with 6,000-year-old trees that died 1,000 years ago, and others that died 2,000 years ago, and others that died 3,000 years ago, and continue to overlap those tree ring patterns to get a fairly precise record of how things have been on Earth for about the past 28,000 years. Well, one of those things that you can do is you can calibrate it to your carbon-14, and that allows us to use carbon-14 dating back to about 100,000 years due to calibration with tree rings. It also tells us when there was more solar activity versus less solar activity, because if you have a lack of carbon-14 at a certain time, then that tells you the sun was more active. If you have extra carbon-14, that tells you that our sun was less active. Similarly for beryllium-10, which is another radioactive species. So here's how beryllium-10 is produced in the atmosphere. You can get neutrons that occur from these cosmic rays. They interact with a nitrogen-14, making an excited nitrogen-15, which decays into a beryllium-10 and an alpha particle and a proton. So here also is the reaction for producing carbon-14. A neutron hits a nitrogen-14, giving you carbon-14 plus a proton. And interestingly, when you make graphs showing solar activity, you end up getting something like a hockey stick graph, which you often see in climate change studies showing Earth's CO2 in the atmosphere and temperature. But you also get a hockey stick pattern when you gauge solar activity, in particular the beryllium-10. This really shows the power of that grand maximum that we had that was particularly prominent from about 1940 up until about 2005. So, the big question: is current climate change being caused by the sun? This is something that has a lot of controversy at the social level and also in politics. So, unlike what's often heard in the media and in political circles, there was actually quite valid scientific justification for believing either that it was or was not caused by the sun well into the 2000s. And there are a number of reasons for that that we're going to get to. But I will first mention that events over the past few years have now caused us to favor one of these paradigms quite strongly over the other. So first, what about these solar variations? So there are a number of things that caused the climate to cool during the Little Ice Age. Lack of solar activity was only one of them. Another possibility, it seems, was increased volcanic activity, which will also cool down the climate. But thereafter, it will cause it too warm again. Once the dust settles and ends up absorbing the sunlight, you end up getting increased heating due to that effect as well. Now, whether the Maunder minimum played a more significant role than the volcanism, we're really not sure at this point. But if the volcanic explanation is correct, this would definitely explain the warming that the world experienced coming out of the Little Ice Age into the early 20th century. Now, there have been a number of attempts to try to model potentially unknown effects. For example, it is believed in many circles that magnetic forcing mechanisms from our sun, when our sun is more magnetically active, can have a big influence on climate. So one attempt is to simply assume that magnetic forcing gives you an effect that is 3 or 4 times greater than the forcing from changes in the amount of sunlight itself. And there aren't very good physical justifications for this in terms of the theory, but interestingly enough, doing so ends up giving you a very nice agreement with how global temperatures have changed over about the past 1,000 years, including the warming trend that occurred during the last quarter of the 20th century. But again, we don't have very good theoretical justification for this, so maybe that's something that we will understand better in the coming years, but it's really difficult to say that this is it when we don't have a good way of understanding why this should be it other than the nice matching in the data. But it is interesting that our sun's magnetic flux has more than doubled during the past 110 years. Now, what about human effects? So, beginning with the Industrial Revolution, humans began emitting a lot of carbon dioxide into the atmosphere at a greater rate than it would be destroyed by natural processes, typically a CO2 molecule in the atmosphere being produced naturally or by whatever process would end up having an average lifetime of about a century or so. But since the Industrial Revolution, we started emitting it more quickly than it would naturally be destroyed. And in particular, the rapid industrialization around World War II and then afterward really caused this to pick up. Now, something that needs to be kept in mind is that carbon dioxide is what we call a minor greenhouse gas. It does not have quite as strong of an infrared cross-section as things like water vapor and CO2, or sorry, methane. In fact, methane is a really, really nasty one in terms of a CO2 cross-section. The good thing is that methane does not last long in the atmosphere. A typical methane molecule might last a few years or so before it's destroyed. But carbon dioxide, unlike water vapor as far as we know, has been increasing in the atmosphere. So even though it's a minor greenhouse gas, the fact that it is increasing is a potentially major concern. So first, let's show this graph showing the atmospheric carbon dioxide in over about the past 400,000 years. Now, the spike right here is due almost entirely to human activities. We know that because of the ratio of carbon-13 to carbon-12. When carbon dioxide naturally goes into the atmosphere from various processes like volcanism, it's a certain ratio of carbon-13 to carbon-12. But when it happens due to the burning of fossil fuels, it's a very different ratio of carbon-13 to carbon-12. And the spike shows the fossil fuel ratio. So that's how we can really nail down the exact cause of that. There is no debate about that. That is completely incontrovertible. The spike in CO2 is almost entirely due to human activity. Now another graph I'd like to show you is a relatively famous graph showing how carbon dioxide has increased over time, particularly since the 1950s. In fact, it originally started increasing at approximately an exponential rate, but starting around the 1980s, it became a roughly linear rate. But it's not so much that to which I want to bring your attention. It's the bumps in the graph, the oscillations in the graph. So this is taken at Mauna Loa Observatory in Hawaii, which is in the tropics, as you can imagine. But this is actually showing bumps nonetheless. So why would the amount of CO2 in the atmosphere change throughout really the course of the year? So here's the thing. Keep in mind that about 90% of the world's landmass is in the northern hemisphere. And as a result, you're going to have most of your forests in the northern hemisphere. Well, what happens? During the summer, a lot of matter is decaying in the forests and everything, and that's going to release a lot of CO2 into the atmosphere as the matter decays. But during the winter, the temperatures are cooler, and that's going to slow down. Now, you're also dealing with less use of CO2, so some of that balances out. I don't know exactly how that balances out in terms of the seasons, but I do know that that general changing in the amount of decay in the forests is the reason for these bumps. Now, what that should also cause you to keep in mind is that as the world's temperatures change, you're going to get an increased amount of CO2 in the atmosphere because of this more rapidly decaying plant matter and everything. So that's just one of those things that is well known also in climate circles, that as temperatures change, you are going to end up getting more CO2 in the atmosphere. We're going to come back to that in a graph very soon. Now, what is the direct effect of CO2 on temperature? Surprisingly, this is actually fairly well known, and the number is probably a lot lower than what most of you have heard before. Every time you double the amount of CO2 in the atmosphere, you should expect global temperatures to increase by 0.4 degrees. So we have not yet doubled the amount of CO2 in the atmosphere since the Industrial Revolution. In fact, based on the increase since the Industrial Revolution, you would expect that global temperatures should have risen by 0.3 degrees. So, well, keep in mind, the beginning of the Industrial Revolution, we were in the middle of the Little Ice Age, so temperatures were a lot cooler than normal. So we climbed out of that, and since then temperatures have, of course, been going up over time. But nonetheless, this is a logarithmic effect in terms of CO2 and temperature. The reason for this, by the way, is because the wavelengths that CO2 absorbs in the atmosphere are pretty much saturated. CO2 has just about saturated its effect. And when you get close to saturation, in order to get a linear increase in temperature, you need an exponential increase in what's doing the absorbing. So that has actually not been going on since the 1970s. So you might wonder, why is everybody panicking? Well, something that is well known in climatology circles, but not well known in the media or in political circles, is that the minor greenhouse gas CO2 has an effect on atmospheric water vapor, a major greenhouse gas, and that effect occurs due to the changing partial pressures of the gases in the atmosphere as you increase the CO2 in the atmosphere. So as you increase CO2 in the atmosphere, you also increase water vapor in the atmosphere, and that is something that would potentially cause major greenhouse concerns. Now, in truth, we really do not know the exact feedback between CO2 and water vapor and the resulting cloud formation, all of those combined. It is generally believed, in particular according to computer simulations performed by Richard Lindgren, the chief climatologist at MIT in the late 2000s, that this will result in enough cloud formation that the actual warming effects of the water vapor end up getting canceled out by the increased reflection of the clouds. So according to Lindgren's group, you're simply going to get on average about a 0.5 degree temperature increase per century as CO2 ends up continuously going into the atmosphere. Now, more recent computer simulations, though, have led to some very interesting results. In 2019, some detailed computer simulations at first confirmed Lindgren's results until you get up to about 1200 parts per million, which is about 3 times what they are in today's levels. At that point, the formation of the high-altitude altostratus clouds, which help to reflect a lot of the sunlight, ends up actually not occurring so much. Instead, something else happens and those clouds end up not forming. And when that happens, you end up getting a relatively rapid increase in global temperatures of about 5 degrees Celsius. So that's something that would potentially be encountered in the 22nd century if we don't really start paring back our CO2 levels in the atmosphere now. And yeah, it's not something that's going to affect us so much, but we need to keep future generations in mind. So what would that end up doing? Well, that would end up returning us to what it was like during the peak of the Cretaceous period and during the peak of the Eocene epoch, which is a period of about the Eocene epoch when this peaked was about 55 million years ago. And you got rainforest stretching to Alaska. There were crocodiles living off the coast of Alaska, stuff like that. And I mean, you can figure that the resulting sea level rise would not be good for our coastal communities. Now, I do want to show you a graph that has been often used by so-called deniers in, concerning global warming and climate change. The graph itself, there's nothing wrong with it, but you should nonetheless keep in mind that CO2 itself is a greenhouse gas, and increasing it would be expected to increase global temperatures. So here is the graph. So the main point on the graph is, so notice that time increases going toward the right, where 0, which is right now, is today, and we're talking about thousands of years ago, going toward the left. In red shows the temperature, and blue shows the amount of CO2. And generally speaking, what you see are spikes in temperature before you have spikes in CO2. This graph, ironically, this was one of the original graphs on which a graph was brought into the famous movie Inconvenient Truth, and Al Gore pointed out his graph just showing, it's like, yeah, look how CO2 ties to temperature increases and we should be really scared. Now, of course, keep in mind that Al Gore is not a climatologist. He has practically no scientific training or really scientific knowledge on these sorts of things, so he's not necessarily good at really looking into the details of scientific data. He's a propagandist, so that should be kept in mind there. But something that, again, should also be kept in mind is that CO2, while it's a minor greenhouse gas, is a greenhouse gas, and just CO2 increases themselves would be expected to increase global temperatures at a rate of about 0.4 degrees per doubling of CO2, and that's even ignoring any water vapor feedback effects, which we're starting to realize will potentially become quite serious after a certain point. Now, in spite of what you might have heard, the rate of global warming actually peaked in the 1980s and the 1990s, and it actually started slowing down after that. So you sometimes hear global warming is accelerating. Well, over the past few years it has been accelerating, this video being made in 2020, but it was not accelerating during the 2000s when the media was talking about how global warming is accelerating and Al Gore came out with his Inconvenient Truth movie. In fact, it was during that time that global warming was pretty much flat throughout from about 1997, before the El Nino spike of 1998, and really up until about 2015, there was no statistically significant warming trend. That did change in 2015, as we're about to mention, but there was no statistically significant warming trend during that time. Now, taking a longer period, though, you definitely do get a statistically significant warming trend, and since the 1970s, that has been on average about 0.13 degrees per decade, or about 1.3 degrees per century. In fact, the most recent results over the recent years are pointing toward more about 1.4 degrees per century. So, nonetheless, this is not a reason not to be concerned. These numbers might sound relatively small, but that even just that can have a significant effect on global climate and even the weather over long periods, especially if you talk about century after century. So it's never too early to start realizing what we need to change in order to help future generations on this. Now, the current rate of warming is, as I mentioned, about 1.3 degrees per century. There is a high uncertainty on that, at least if you're talking about over the past like 1 to 2 decades, an uncertainty that's roughly as large as the number itself. So it is statistically significant now, though, especially over the past few years. So climatology over the next few decades will be dedicated to determining whether the low rate will continue or whether it's actually going to start to pick up as human influences become ever more important. Now, the 2 warmest months on record were February and March of 2016. And that followed the strongest El Nino in known history. El Nino is a warming of the Pacific Ocean waters. So this is showing a graph of that where the red and orange denote warmer than average temperatures. Temperature anomaly, you're talking about a departure from average, where average is kind of this teal color. And where you see the blue, it's cooler than average, red warmer than average. During El Nino years, the world's temperature is higher. During La Nina years, the world's temperature is a little bit cooler, though it is during La Nina years where you tend to have a lot of hurricanes in the Atlantic Ocean for reasons that are completely different. They more have to do with the lack of shearing effects between the trade winds and the winds in the upper atmosphere. But yes, the El Nino of 2015 into 2016 was the strongest in known history, and that led to 2016 being the hottest year that since modern records began. Now, I should mention that 2019 was actually probably the second or third hottest year on record since we started having modern satellite keeping records. And why that was significant is for a number of reasons. One, it occurred during a period of low solar activity. Remember, when you have high solar activity, that can bump things up a couple tenths of a degree. But the temperature was about half a degree above average, and that actually made 2019 the warmest year on record without a significant El Nino event. In fact, I should mention that it's by far the warmest year on record without a significant El Nino event, so that's something to keep in mind. In fact, February of 2020, which had a temperature anomaly of 0.76 degrees, is the warmest recorded month without a significant El Nino event. In fact, it's the warmest recorded February ever, and it's like the 3rd or 4th warmest month period, but the other 3 warm months were during the El Ninos of 2015 to 2016 and the El Nino of 1997 to 1998. So this is a histogram of the temperature anomalies over the past 40 plus years since the satellite ended up going up. This was sent up, and these data are kept by the University of Alabama at Huntsville, and they have a satellite system that measures the black body radiation measurements from Earth's surface. That's important because a lot of what you come across that show very strong temperature departures from normal and stuff like that are based on other measurements. For example, temperatures in the upper atmosphere, or temperatures according to ocean buoys, which themselves are not considered to be very reliable. And that's the type of thing to keep in mind, but this is just direct black body temperature measurements. And one of the things that stands out to me in this is that we have not had a below average month since early 2012. that makes this easily the longest period since the records started being taken without a below average month. And also, typically after a solar minimum, you end up getting some cooling. There was a very significant protracted solar minimum in 2007, and that led to early 2008 being rather cool. In fact, 2008 as a year was a cooler than average year. But in 2018, this was the result of that solar minimum there. That's as cool as we got. And since then, things have started to warm up, even though we're really still in a solar minimum. There are, as I speak, there are currently no sunspots on our sun. So nonetheless, temperatures have continued to get warmer after that. This scares a lot of people because it is difficult to explain naturally. In fact, there are a number of ways of explaining the warming that occurred during the last part of the 20th century. So skipping ahead, there was a period that we call during the late 1980s, well actually throughout the 1980s and the 1990s, when there was a particularly strong Pacific multi-decadal oscillation. And this ended up leading, this oscillation over the centuries has been known to be associated with warmer than average global temperatures. And it was quite strong during this time. And also remember, this time was right in the middle of the most significant grand solar maximum, which is a period of higher than normal solar maxima. We call that a grand maxima. This was the strongest grand maximum of the past 9,000 years. So those two combined could potentially explain Earth's temperature increase during the last quarter of the 20th century. But here's the thing. The Pacific multi-decadal oscillation went into reverse in the late 1990s, and the big grand maximum peaked and then came to an abrupt end in the mid-2000s. In fact, a lot of people are thinking that we might end up going into a grand minimum. The Maunder minimum was an example of a grand minimum, though this one hopefully won't be that bad. But the Dalton minimum was another grand minimum. But there are some solar scientists who think that we might be about to go into a grand minimum. So based on all of this, you would expect that if it was all of this that was causing Earth's temperatures to increase during the last quarter of the 20th century, then they should be going into reverse right now. But they have not been doing that. In fact, I remember in the late 2000s, the various groups who contended that whether the global warming was caused primarily by natural events versus anthropogenic causes, that is, human causes, said that, well, that we can make a prediction. If it's caused by natural events, then we expect that during the 20-teens, temperatures should start to get cooler starting around the early to mid-20-teens. Instead, they've done the opposite, whereas the people who believed that global warming was primarily due to human activities, they predicted that during the 20-teens, temperatures would just continue to get warmer, that this period of leveling off during the 2000s would go away and temperatures would start to increase again. And my view is that the ability to have your theory make predictable results, give predictable results, is the hallmark, at least, of whether you're on the right track. And the fact that the reality has been in much better accordance with the predictions of those who in the late 2000s believed that most of the global warming was man-made indicates to me that that is the theory that is more on the right track than the idea that it's primarily caused by natural oscillations. Now, that's not to say that that most of the warming during the latter part of the 20th century wasn't natural. It could have been completely natural, or almost completely natural, with only a small effect due to human activities. But it's difficult to maintain that that is the case right now when those known forcing effects have gone into reverse. Now, given that the Arctic regions are covered with ice for a large part of the year, and ice is highly reflective, a small change in the average temperature of Earth can result in quite significant changes in the Arctic regions. For example, consider this graph of Tromsø, Norway, which I believe, just above the Arctic Circle. It's pretty close to 70 degrees north latitude, and we're talking about very significant changes in average temperatures, in this case in the month of June, over the past 10,000 years. And the graph isn't quite updated. If you were to put in today's data, you would probably take it up about a degree to a degree and a half. But this mainly is to show you how rapidly things can change just when you're talking about small changes in the rest of the world. Now, here's another graph in Northern Ireland, and here we're talking about changes on the order of a degree to a degree and a half from one decade to the next, just based on relatively small forcing mechanisms in the rest of the world. So, at this point, it's difficult to predict how things are going to occur in the remainder of the 21st century, because we're still kind of waiting for the best computer simulations to conclude what exactly is the effect of increasing water vapor in the atmosphere. That's something that should end up becoming a bit more clear in the mid-2020s. Now, throughout this, I have kind of given some caveats in contrast to some of the various alarmist scenarios that you've probably heard throughout the media. I try to keep things as scientific as possible, and also try to kind of just keep everything straight whenever I can. So you might wonder, is this a reason to ignore some of these alarmist warnings about human-induced climate change? It's definitely not. I'm just mentioning that the currently available science does not necessarily justify the highest alarm scenarios that you might have, because it really is difficult to model cloud formation in the current generations of supercomputers. And it could be that the water vapor feedback is a very strong positive feedback loop, and that would potentially be very bad. But at this point, we do not really have very good evidence for that, other than what might happen if we end up tripling the amount of CO2 in the atmosphere at this point. But nonetheless, there are other very significant impacts that have nothing to do with global warming that we also need to keep in mind. And even with those in mind, even if that tripling effect resulting in suddenly a 5-degree warming due to lack of altostratus clouds forming in the upper part of the troposphere, even if that ends up not being the case, if we continue increasing greenhouse gases at the current rate, then you're still going to be talking about very big effects over the coming centuries. Now, the non-greenhouse effect scenarios mainly involve Earth's oceans, and that's what I think we should really be concerned about in our current scenarios. In other words, within our lifetimes, as opposed to our children's and grandchildren's and great-grandchildren's lifetimes. A very harmful effect of considerable fossil fuel use, aside from the obvious environmental pollution, is the fact that when you increase CO2 in the atmosphere, that changes the balance of how much of that CO2 dissolves into the oceans. When it dissolves into the oceans, it becomes carbonic acid, or at least a lot of it becomes carbonic acid. That can devastate coral reef systems, which, as you know, form the backbone of oceanic ecology in a lot of ways. And in addition to just bleaching out some of these coral reefs, they can also change the behavior of the creatures that live around them, and that throws the entire ecosystem off. And this is something that we're already seeing happening, and I anticipate that this is going to be one of the really big worries in our lifetimes. It's not going to gain as big of headlines because of the fact that you can't really see the human devastation so directly as you might be able to see in the destruction of a hurricane, which the link between hurricanes and human-caused global warming is tenuous at best, because just for other scientific reasons, the fact that the temperature differences in the atmosphere are different when you cause global warming with CO2 versus natural causes. In fact, it could be that, in fact, it's looking probable that increasing just CO2 and causing warming that way would potentially decrease the intensity of hurricanes, but that's a different scenario. But in the case of the oceans increasing CO2 and the carbonic acid in the water that results from that is going to be potentially devastating throughout the rest of the century, and I think that's something we really need to turn our attention to. Now, aside from all of this doom and gloom about how we're destroying our oceans and how we're potentially going to increase the temperature of our planet by a significant amount, there's also, going back to the astronomical scenario, something else about our sun's effect on our climate. Um, every billion years, our sun becomes about 10% brighter. And that's continuously been the case, at least according to computer simulations and as far as we can tell with other stars, based on their ages and where they are in their evolutionary life cycle and their brightnesses and all of that. And the realization is that when our sun first formed, our solar system first formed, Earth should have been quite a bit colder. So, because our sun was a good 40% fainter. So the question is, why weren't we an icebox? Now, it turns out that we actually were occasionally an icebox when things just weren't working out so well. But when Earth first formed, we had a much thicker atmosphere. We had a lot more volcanic activity than we have nowadays because, again, we had a lot more radiogenic heating in the interior, so that caused a greater amount of volcanic activity. And in particular, there was a lot of methane in our atmosphere early on. And methane, as we mentioned before, is an extremely powerful greenhouse gas. And there was also more water vapor and carbon dioxide in the atmosphere as well. So the fact that our sun used to be very faint and we should have been very cold was known as the faint young sun paradox, but now we think we have a solution to that in terms of the fact that our atmosphere used to be much thicker. So this concludes our sun PowerPoint. Hopefully you found it informative and hopefully even enjoyable at times, even though certainly going over a PowerPoint on video can be quite dry. But in particular today we focused on how our sun affects situations on Earth, in particular various types of solar activity, and also the effects on climate, and both present and past. So if you have any questions, please let me know, and please stay tuned for our next PowerPoint and video going over the various types of stars that are out there. Thank you.